Welcome to a read along with Dr. Powell in the book Discrete Perspectives in Mathematics. This is section 4.2 on permutation arithmetic. So we're going to be doing operations with permutations. What are permutations? Well, here's a definition. A permutation is a self-bijection. So if we have a set, say A, it's a bijection from a set to itself. Um, So, um, for instance, let's look at this example right here. This is a function from a set of 1, 2, 3, 4, 5 to itself, and it's injective because um, the everything that goes to 5, there's only one thing that goes to 5, only one thing that goes to 4, only one thing goes to 1, only one thing goes to 2, only one thing goes to 3 here. And so it's injective and it's surjective because 1, 2, 3, 4, 5 are all hit. So this is a bijection. Now there's various ways of picturing this bijection. For instance, you can think 1 goes to 5, then you can think 5 goes to 3, and then 3 goes to 1, and it goes in a loop, pictured by this diagram here. So 1 goes to 5, just like 1 goes to 5, and 5 goes to 3, just like 5 goes to 3, and 3 goes to 1. But if we do this, we kind of get a cycle out of the function assignments. So because we can kind of go around, because every codomain element is really a domain element. And everything is only hit by one other thing. And we get these loops happening here in the definition process when we have a bijection from a set to itself. So, and likewise here, 2, 4, and 4, 2. So we get a loop right there. So this permutation is made up of two loops. We can represent them in a picture like this, or even I just write them out like this. 1 goes to 5 goes to 3, and as soon as we hit a parenthesis, we go around to the beginning of the parenthesis. So 1, 5, 3, then 2, 4, 2 goes to 4, then back to 2, and so forth. It's another way of doing it. Let's see. We could also represent it this way, which is really the same as this. 1 goes to 5 goes to 3, and then we just know we loop back to 1, and similarly over here. We could also do it this way. We could just line up the domain 1, 2, 3, 4, 5 and the codomain 1, 2, 3, 4, 5 in the same order and just draw arrows. 1 goes to 5, 2 goes to 4, 3 goes to 1, 4 goes to 2, 5 goes to 3, and we kind of see the self-bijection happening in that way. So there's various different ways of looking at a permutation. And different pictures actually help us to see different aspects of that permutation and different things we might be useful to us. Now let's talk about an operation that we can do between two different permutations. That is composition, meaning we can take one permutation and do it, and then after that permutation, do another one on top of it afterwards. So these are functions. So composing just means do one function then the other. And it's a way we can put them together and we end up getting a new permutation out of it. So for instance, the red one is F, and we do that one. So 1 goes to 5, and then we do the blue one, G, so down. Notice that represents this black arrow here. What about 2? 2 goes to 4 and to 3. See, so then just directly 2 goes to 3. So these two permutations, one followed by the other one, can be put together into a new one, where the act is just simply taking the path that goes all the way down to the bottom, starting from here, and just straighten it out into an arrow here. Okay, so now we just this is just an example of we can write cycle notation down for this combined permutation here. That happened because of composition just by following this right here. So 1, 5, 5, 4, 4, 1. So back to 1 again. And so that forms a loop 1, 5, 4, and then 3, 2. See, 3 goes to 2, and 2 goes back to 3. Okay. So, or we could do it the other way. We could do G, which was this guy. Let's do it first and then the red one last. Notice when we do that, we actually get a different resulting permutation, which has a cycle notation of 1, 4, 2, 5, 3, if we follow it. 1 ends up going to 4 here, whereas 1 actually went to 5 in the end here. So really, composition, if we change the order, we get different permutations. So f of g is different than g of f. So composition is not commutative. That means that you can't reverse the order. Like with addition, like 2 plus 3, you could say it's the same as 3 plus 2. However, with composition, like in your opposing, these things are not the same. You cannot switch order. Order is important. Okay. All right. So what we're going to do is we're going to take the set of all permutations on a set. So, or just say the collection of all permutations on a set A and call it S sub A here. All right. So let's suppose that that means the collection of all permutations on a set A. And what we've just done is we've just seen that this set has a composition structure on it, meaning we can take two permutations, compose them, and get another one out of it. So composition is like a binary operation on this set of, or this collection of permutations. All right. So what we're going to do is we're going to look at, in order to study kind of the permutations on the set a little better, we're going to categorize them into chunks, well, which will come from fibers with that happen from a merge. And this merge is going to preserve composition. So we're going to create a merge, and then we're going to discuss why it preserves this operation of composition, of composing. Okay. So as we say here, we need some kind of mechanism for choosing which permutations will go where in the merge, which ones will be chunked with which other ones. So let's take a look at, we'll just kind of look at a permutation right here. Let's call it G. And notice that as we order it, so let's suppose we order our elements this way, 1, 2, 3, 4, 5, 1, 2, 3, 4, 5, and we just draw arrows. Notice as we draw arrows, we have 2 hits going on right here, or 2 crossings of these straight arrows. So if we have ordered our elements, and this is a finite set, 1, 2, 3, 4, 5, going this way, then this idea of counting the number of crossings with straight lines is a well-defined idea if we kind of had fixed some ordering of the elements. So we're going to be looking at that, and we're going to actually be categorizing our permutations in the following way. All the ones that have an even number of crossings in such a diagram, and all the ones that have an odd number of crossings in such a diagram. So we just have 2 fibers here. So we've emerged with 2 chunks in it. And great. Now we're going to discuss, okay, does that preserve composition? Well, let's just look at a composition right here. Let's suppose we do F and then G. So F has 7 crossings, G has 2 crossings. All right. Now we can look at this. Okay, so here we kind of draw out what it looks like with just removing the middle numbers, but it has the same kind of shape as this right here. Now let's even go further and just straighten everything out. Now when you let's kind of thinking about the straightening mechanism, because we straighten then then we can kind of count how many crossings we have here. All right. Now, this is also an interesting idea, because how is it going to preserve the operation? Because we'll need a composition type operation between 2 things, right? Even and odd. So we kind of have something needing to happen there. And here we kind of think, okay, like right at first, like F has odd and G has even. And then right here, we straighten these out and count it again. We have 7, 7, so it's odd. So let's kind of think about the procedure for a minute of what happens when we straighten out. When we straighten out, we kind of have like a hump. So like a straight line here, and we have a hump. This hump's going to kind of come in and straighten out. And see right here. Okay, so we have this crossing some places and this crossing some places. Like this crosses right here, this crosses right here. But if we straighten out, notice that this hump is moved over here. And if we straighten this hump is moved over here. It's kind of like this picture right here. We're kind of like taking something and moving it across the line. This is like the only thing that really happens to remove crossings as we straighten out, is this basic type of idea. So, but every time we do this, notice and move it through, notice that we've actually changed the number of crossings by 2 as we move something through like this, because it's just a hump moving through. So really, we should be, so really what we should do is we count all the crossings right here, 7 plus 2. And then if we were to, so which is 9, so there's 9 crossings, but as we straighten out, we get 7 crossings, which should make sense. We subtracted by 2. And if there were lots of ins and outs, we could have even had more, but we just subtract by a multiple of 2 until we get how many crossings there are of the composition. So it kind of, so what it kind of looks like, but that works, right? Because because if we subtract by an even number, and if it's odd, it's going to stay odd, or if it's even, we subtract by even, it's going to stay even. So that actually looks pretty good. So the straightening process is okay. That actually kind of gives us a sense that composition, it works well with composition here in counting crossings if we just think of it as being even or odd. In fact, kind of what we're doing is thinking about, we're kind of turning, via this merge, we're turning composition into straight addition mod 2 in Z mod 2. Like even numbers is 0 bar and odd numbers is 1 bar. So here's a little diagram to illustrate what's happening. So here we have our collection of permutations. All right. So we can take a permutation and we could count the number of the number of crossings in a composition. And then, or we could straighten them out and then count the number of crossings. And then really this is just saying, we're just looking, is it even, is it odd, whatever. That's kind of what we're doing. And notice how the statement that it's commutative just means it should be the same both ways, which we just kind of discussed up there, which actually ensures that this diagram really would be a commutative diagram. Let's kind of look at really what's happening here. So composition really has 2 things happening, right? So we straighten the crossings into 1 permutation, then we count the result, and then we see if it's even or odd. All right. Here, we just count the number of crossings for each permutation that's stacked, and we send it over here. So we have a number in Z and another number in Z. And then we kind of see if, well, okay, is this odd or even? And then we take odd or even, and then we add, the kind of the result to get here. So kind of, this is a description of what we were talking about to make sure that that actually worked. Kind of like as we were straightening these crooked crossings and getting this, notice that we realized we were just always just changing the number of crossings up here by an even amount. And if you change by an even amount, it actually will stay. If it's even right here, it'll stay even. If it's odd right here, it'll stay odd, which is kind of the same statement as saying this whole diagram really commutes. But this diagram commutes. Look what's actually happening. We have an operation here and an operation here. This is addition. and this is straightening crossings, right? So this is the operation of composition in SA, and this is the operation of addition. And notice that because this diagram commutes, we actually have a preservation of the operation. So, so chunking this way actually preserves composition and turns it straight into addition in mod 2 arithmetic. You could even think of it this way, right here. So even, so here's a table which actually is exactly the same table as in mod 2 with a plus, but here we're using a composition symbol because even plus even is even plus odd is odd plus even is odd, and odd plus odd is even. So even with compositions, if we take an even permutation and compose it with an even permutation, we should get an even one. Even one with an odd one should get an odd. Odd with an even should be an odd, and odd with an odd should be an even when we do composition. And this is a symmetric table, so it doesn't matter which order we do it in. Here, this will work. In fact, we're turning composition into an operation addition, which is commutative. So this idea of even odd is a commutative one, even though composition itself is not. But after we chunk in this way, it becomes commutative. Okay, thank you so much for watching that. That concludes subsection 4.2.2. So we did the first two subsections of section 4.2. Thanks for watching.